So, now today we will see some problems based on this amplitude modulation and the range of the line of sight communication. So, let us first start with the calculation of range of a line of sight communication. So, range of a tower which is used in line of sight communication. So, first of all, let us see, this is the curvature of earth. This is the curvature of earth and we have a tower. So, this is the tower transmitter, that transmitter is installed here. So, what happens if I draw a tangent from this on the surface of earth? You see this tangent is here and this is here. So, on this curvature, all this region is within the range and the region beyond this cannot receive the signal. So, this is the range. So, this is a highly exaggerated diagram. So, you see, let us join this point, 2 points, and this is suppose R2 and this is R1. You draw the normal on this, and so this normal passes through the center of earth. This is C. Now, this height is h. So, this is a highly exaggerated diagram. I can neglect this distance. So, suppose I say this is O and this is P. So, P. So, you see this is a right angle triangle and this is also 90. So, this is also a right angle triangle. Let us assume this R as the radius of earth. This height is h and this is suppose P. So, this is P, the top of the tower. So, applying Pythagoras theorem here between P, R1 and C. So, we have this P R1, that is P R1 square is equal to R1 C whole plus this square plus this square plus this square is PC square. So, P R1 square, this is equation number 1, and we can separately find out P R1 square by using this triangle. Let us write it here. P R1 square, that is equal to, suppose this distance is negligibly small. So, this height is h. So, h square plus this. Suppose I denote by small r the range of this radius. This is a circular region. So, radius, that is the range r. So, this is r square. So, we will write P R1 square from here as h square plus r square plus R1c is radius of earth whole square and PC is again h plus r whole square. So, this is the relation. If I solve this, I will get h square plus r square is equal to here h square plus r square plus 2hr. You see this cancels out, h square cancels out. So, we have r square here, that is equal to 2hr, implies r range is equal to root over 2hr. So, if we have a tower on the surface of earth, you see on the surface of the earth, if we have a tower, that is a transmitter fitted on a tower, then the range to which it can cater its services, the signal can be transmitted, will be in this circular area, that radius is equal to under root 2hr, where r is the radius of earth and h is the height of the tower. So, this is the expression for the distance to which, the radius to which the signal can be transmitted in this line of sight communication. So why its name is line of sight means from this tower the maximum distance that can be seen on the surface of earth is up to R1 and up to R1. So within the line of sight all the regions can be comes under the range of this communication. So now let us see a problem through it. Now let us take an example in which we will find the range of a communication system in which we have two towers. So find the maximum distance between 2 points on earth which can receive signals from any of the tower if we use two towers of height H1 is equal to 80 meters and H2 is equal to 320 meters. So suppose we have to cover a maximum range. So what we have done, on the surface of earth we have installed two towers. This is of H1 height, that is 80 meters, and you see this tower can go to a maximum distance here. So again I have one more tower here installed. So we have installed two towers. So you see this, what is the maximum position of 2 points? Suppose this tower can cater people in this region and this tower can. So what is the farthest distance between 2 points which can be, where signal can be transmitted with the help of these two towers? So these two towers are here we are using to extend my range to the maximum possible range. So the question is, what is the maximum possible range which can be achieved by using two towers? One tower has a height of 80 meters, another tower has a height of 320 meters. Let us see this problem. So now let us see, this is the curvature of the earth, and you see this is point A here I have assumed. So this is my point B, and this is one tower. This is a highly exaggerated diagram. So there are two towers I have installed, and this tower of height H1 is equal to suppose 80 meter, and this tower H2 is equal to 320 meter is there. So the farthest distance this tower can cater is at A, and here this tower just this is tangent and this tower. So you see this region can be catered by this tower, and just beyond this it comes under the influence of this tower. So the farthest distance to which A and B lie will be this R1, and so this is R1 and this is R2 and this is R2. So the range, the maximum range due to these towers, due to these two towers will be 2 times R1 plus R2. So now let us calculate individually what are the range. So R1 range is given by under root 2 HR, where H is the height of the tower and R is the radius of the earth. So this is 2 times height, this is 80 meters, and radius of the earth is approximately taken as 6400 6,400 kilometer. So in meters it is this. So 8 into 2, 16, 16 into 64 is this, and you see 3, 4, 5, 6, that comes out to be 10 to the power 3. This is 4 into 8 kilometers, that is 32 kilometers. So the range of this tower is 32 kilometer. Similarly, we can find the range of this tower H2 as under root 2, this is H1 and this is H2 R. So root over 2 times this height H2 is 320 meters. 320 into 6400 into 10 to the power 3. That is again 64 into 64 root into 3, 4, 5, 6, that is 10 to the power 3 meters. That comes out to be, this is 64 root means 8 into 8, again 64 kilometer. So this is 64 kilometer. Its range is 32 kilometer, its range is 64. So the maximum distance to which the total extended range AB is equal to 2 times R1, that is here 32 kilometer plus 64, that is 2 times 6 and 96 kilometers. So 96 into 2 is 192 kilometer. So 192 kilometer will be the range, the extended range, if we use these two towers. That maximum range can be covered each 192 kilometers. This is how line of sight, this is the range of this line of sight communication. Now let us take one example to see how amplitude modulation takes place. So this is an example. So during amplitude modulation, we have found that the maximum amplitude is A max and the minimum amplitude is A min in the modulated carrier wave. So the maximum and the minimum voltages of an amplitude modulated wave, AM wave, amplitude modulated wave is given by A max and A min. Find the modulating index mu. So by this we want to know how this modulation, amplitude modulation is taking place. So this is what we want to do. So now you see, let us draw, this is the time is plotted here and here the voltage is plotted. So this is voltage plotted here. This is positive side and this is this negative. Now suppose this is my amplitude of carrier wave, IC AC. This is AC and this is minus AC. AC and minus AC. Now suppose the modulating signal, suppose AC, the carrier wave is given by AC sin omega ct and the modulating wave is given by AM sin omega mt. So this is the amplitude AM and AC of this wave. So AC is represented here, and so you see here this is AC, this is AC plus AM, AC plus AM, and you see this becomes AC minus AM. You see AC plus AM is here, AC minus AM here. Similarly, we will have here its negative quantities will be here. So now what I say, that the amplitude modulated wave So you see, when I am adding up this carrier wave and this modulated wave, then the modulated carrier wave is given as AC plus this AM sine omega MT sine omega CT. So you see, the amplitude of the modulated wave will be AC plus this signal wave will be added. So we have our wave like this. Our wave will be oscillating like this. This is the carrier wave. So you see, please here, concentrate here. In this whole region you concentrate. The maximum amplitude, this is the carrier amplitude. This is AC is the carrier amplitude. This is the carrier amplitude. So what happens? The maximum amplitude is AC plus AM and the minimum amplitude is AC minus AM. So A max is carrier amplitude plus AM and A min is equal to AC minus AM. So this is maximum and this is minimum, and this diagram is very important where it can be shown that how the modulated wave goes on. You see, previously when there is no modulation, the waves has the constant amplitude of AC. Now when I have modulated it, its amplitude varies from AC plus AM to AC minus AM. Here is the minimum amplitude and here is the maximum amplitude. This is what a modulated wave is. One more important point. You see, in the amplitude, this wave, you just imagine this wave. This wave carries the signal. The envelope of this amplitude modulated wave carries the signal. So this is how the signal. So its name is amplitude modulation. Please see this diagram very carefully. So now let us see how A max and A min can be expressed in terms of modulation index. So we define modulation index mu as AM by AC, and generally it is less than 1. So A max becomes AC plus AM is mu AC, that is we get AC 1 plus mu. A min will be AC minus mu AC. So minus AM is mu AC, that again comes 1 minus mu. So let us divide these two. So we have A max by A min. You see, A max is the maximum voltage and A min is the minimum voltage, is equal to AC 1 plus mu by AC 1 minus mu. These two cancels. So we have A max by A min 1 plus mu by 1 minus mu. We want mu. So what we do? we take A max minus A min by A max plus A min using componendo and dividendo. So here what we will get 1 plus mu minus 1 minus mu by here 1 plus mu then minus then plus 1 minus mu. So this will be equal to, you see here minus, so here 1 will cancel, mu plus mu, that is 2 mu, and here this mu will cancel 2, and so 2 will cancel. So mu, that is the modulating index, becomes A max minus A min by A max plus A min. You see this is less than 1. So this is the modulating index mu, that if I get the maximum amplitude and the minimum amplitude of the wave of the voltage edge, then we can calculate this modulation index by this quantity. So now we have a problem in which a carrier wave of peak voltage 12 volt is used to transmit a message signal. What should be the peak voltage of the modulating signal in order to have a modulation index of 75%? So what is given in this problem? Mu value is equal to 75% means 0.75. We have been further given 12 volt as the peak value of the carrier wave. So AC is 12 volt. Next, what should be the peak voltage of the modulating signal? That is AM is required. So it's simple. Mu, that it's this problem is just the definition of mu. Mu is the peak value of the signal wave and the carrier wave. Implies here mu is 0.75, signal wave is required, and this is 12 volt. So this AM is equal to 0.75 into 12 volts. This is 9 volts answer. So now let us take one more example of amplitude modulation, where the modulating signal is a digital signal. You see, in amplitude modulation, so the signal wave can be an analog or can be a digital signal. So you see here, a modulating signal is a square wave as shown in the figure below. So this is the modulating signal given. Here the voltage, this is voltage plotted, and this is varying from 1 to -1. So this is up to 2 seconds shown. So in 1 second, for half second the signal voltage is +1, then becomes -1, then +1, then -1. So this is your digital signal given, and the carrier wave is given by this CT. CT is the carrier wave given. So we have to sketch the amplitude modulated waveform and what is the modulating index. So what we do? So this A max which we calculate is actually given by AC plus AM, and we have A min as AC minus AM. So AC is here, AC is given as 2, so 2 plus the maximum signal is 1, that is 3 volts. So we have 3 volts as the maximum, and we will get A minimum as 2 minus 1, that is 1 volt. So my carrier wave, my modulated carrier wave will vary between 3 volts and 1 volt. And the modulation index which we have to calculate, that mu is equal to AM by AC. You see the maximum amplitude is constant here, that is 1. 1 by AC, that is 2, is equal to 0.5. So the modulation index is 0.5 and the maximum amplitude is 3 and the minimum amplitude is 1. Now let us see how to draw the modulated carrier wave. That means how the carrier wave will be modified according to this some digital signal. You see, this is not 0 and 1, this is 1 and minus 1. So this is a rectangular waveform. Let us see this. Please take this. So before we draw the modulated carrier wave, we require certain informations. Let us write the informations here. A max will be this. We have already calculated it is 3 volts. A mean already we have seen it is 1 volt. Modulation index is 0.5. And what is the carrier frequency? Let us see from this. Omega C, omega carrier frequency is 8 pi. That is 2 pi into the frequency of carrier wave, that is 8 pi. So this pi cancels. F carrier is equal to 4. So 4 times the wave form oscillates in 1 second. So this carrier frequency, that Fc is equal to 4. So these are the required information to draw this modulated carrier waveform. So now let us see how to draw the waveform of the modulated carrier wave. So you see here, first of all we have to find what is the maximum voltage, 3 volts. So you see here, this is the voltage waveform and 3 volt is here, and you see minus 3 volt. Then minimum, that is 1 volt. So this is 1 volt and minus 1 volt. So the within this 3 volt lines, my amplitude will be going and the minimum will be this much. So what we have to do, and Fc is 4, that is the carrier wave frequency is 4. That means in a second it makes 4 waves. So in half second 2 waves. So half second means this is 0.5 seconds and this is 1.5 seconds, suppose. So in 0.5 second it makes 2 complete oscillations. So you see my wave should go from here and its amplitude should, you see, go up to 3 volt, up to 3 volt go, should go, and then it will come to here this minus 3 volt, and you see. So within 0.5 second, you see the modulating signal is 1 volt, this is high volt. So you see the carrier wave was up to 2 volts. This was the amplitude of this carrier wave. So when the voltage is 1 volt, modulating signal 2 plus 1 volt, that means up to 0 to 0.5 second the wave will make 2 oscillations, and that with an amplitude of 3. So the wave will again go like this, the wave goes like this, and you see it comes like this. So you see the frequency is 4, that means it will make 2 complete oscillations in 0.5 second. And second thing, here the carrier wave is of 2 volts, since the modulating wave is 1. So here we have the total amplitude as 3 volts. So it goes up and down. Now here my signal voltage is minus 1 volt. So when I will superimpose this on this amplitude 2 volt, I will get 2 minus 1 is 1 volt. That means it will make 2 rounds, 2 complete waves with this amplitude, and you see it goes like this. So 1 complete and then 1 more complete. You see 2 per 0.5 second it will have 2 oscillations, 2 oscillations in half seconds. So frequency is 4. So frequency is plotted here, and you see that the amplitude here of the signal wave is minus 1. So 2 is the amplitude of carrier wave, and this is the 1 volt is the minimum. So this is A minimum, this is A minimum, and this is A maximum. So again the same thing repeats here. So within this it has to make one complete oscillations. Again here it goes like this, and then again it goes like this, and then again it's here it's -1, so it's like this. So this is the modified modulated waveform. You see the difference. In the previous cases we have taken the analog signal. The signal was continuously here something rectangular. This is also, it's not digital signal, but it's a square waveform. It can be digitized. So then within this square waveform the signal, the amplitude, the signal, you see the envelope you see, what is the envelope? You see this is the envelope. So this envelope carries this signal. This envelope, the amplitude, the envelope of this amplitude carries this signal. This is how we transfer this signal in this. This is how the amplitude modulation takes place. Now let us take one more example to understand the terminologies of the waveform in the amplitude modulated wave. Sometimes the same concept is asked in some different format where students are confused. So the maximum peak to peak voltage of an amplitude modulated wave is 16 millivolts, and the minimum peak to peak voltage is 4 millivolts. Calculate the modulation factor. So here first of all we may get confused with peak to peak voltage and consider this as a maximum voltage. So that is wrong. So first of all we have to understand what the problem says. Now you see this is the amplitude envelope. I am drawing the envelope. So this is the outer, this is the envelope of the amplitude. The actual wave will be moving like this, will be like this. So I am just drawing the outer boundary now. So what I mean by peak to peak is this voltage. This is given as 16 millivolts, and peak to peak minimum voltage is given as 4 millivolt. So Amax maximum voltage becomes 8 millivolts and minimum becomes 4 by 2, that is 2 millivolts. So the common mistake is to consider peak to peak voltage as only 6. So we will say Amax is 16 volt and Amin is 4 volt. This is the common mistakes. So it is modulation index required. So we got Amax and Amin. So by calculating, we will calculate mu, the modulation factor, as Amax minus Amin by Amax plus Amin. This was the result which we discussed in our first problem only. So mu was equal to Amax 8 minus 2 by 8 plus 2, that is 6 by 10, that is 0.6, that is 60%. In terms of percent, 60%. So the modulation index is here 60. So here in this problem you have to remember two things. One, mu is the formula, mu becomes Amax minus Amin by Amax plus Amin. Already we have seen in previous examples. And the calculation of max, that is the half of this peak to peak voltage, and Amin, that is this much, that is half of peak to peak minimum voltage. This notation we should be very careful with this peak to peak notation. So now let us take one example where we will talk about the frequencies of the sidebands. So a 2500 kilohertz carrier wave is modulated by audio signal with frequency span of 50 to 15,000 Hz. What are the frequencies of the lower and upper sidebands? What bandwidth of the RF amplifier is required to handle the output? So what is given here? The carrier frequency is given as 2500 kilohertz. This is the carrier wave, and the frequency of the modulated wave, the signal wave, that is the audio wave, is from 50 to 15,000 Hz. So if I write in kilohertz, kilo means 10 to the power 3. So I will get 0.050 to 15 kilohertz. This is the frequency range of the signal wave, modulating signal. Now once this is modulated, it has to be amplified with an amplifier and then transmitted in the channel. So the amplifier at the transmission end and even at the receiver end, all the amplifiers must be able to carry on this bandwidth. So what is asked, that what is the bandwidth of the amplifier that will amplify that? So second question. So first, what are the sideband frequencies? What is the range of sideband frequencies? It is asked. So let us see, in amplitude modulation, you see, this is here I write carrier frequency. So there will be one lower frequency, that is sideband, that is FC minus F signal, and here there will be FC plus that frequency of modulating signal will be there. So this is called lower sideband, this is called upper sideband. This is the carrier frequency. So in amplitude modulation, here we have this FM. Now FM has here one again 0.050 to 15 kilohertz. So let us see what is these frequencies and what is this frequencies. Now this is the lower sideband and this is upper sideband. Upper sideband. So let us first start with lower sideband. Lower sideband. So lower sideband is given by FC minus FM. So the lower sideband has again here, since the signal has two form, so it will split up into two. This will be FC, this one suppose I call something F1 and this is F2. So F1 will be equal to this one, you see FC minus, so if 15 minus 15, so FC value was 2500, so directly write 2500 minus this 15. So 2500 minus 15 is 5842 kilohertz. This is this much. Next, F2 will be equal to 2500 minus 0.050. So it is something 2, 4, then it will be 9, here something like this will be there. So we will subtract, let us do it. So this comes out to be 2499.95 kilohertz. This. So F1, F2 we got, this is this much. Now let us calculate upper sideband. Upper sideband. Upper sideband is given by FC plus modulating. So again here F1 dash will be there, that is 2500 plus 15, that is 2515 kilohertz, and F2 dash will be given as 2500 plus this one 0.050, that is 2500.05 kilohertz. This is F2 dash. So here F1, and so here again here you will get this F1 dash will be this much, F1 dash, F1 dash and F2 dash. So these are the lower side bands. Lower side band will vary within this and the upper side band will vary within this frequency range. So the bandwidth requirement, for the amplifier is, you see, the amplifier must be able to pick up this F1 and F1 dash. That is, F1 is this, F1 already I have written minus 15, this and this. So the bandwidth requirement of the amplifier becomes, this is the 2515 minus 2485 kilohertz. That comes out to be 30 kilohertz. 30 kilohertz. So you see here that this bandwidth requirement is twice the maximum frequency of the modulating signal. So I hope first you write down this. So thus we see that the bandwidth requirement of the amplifier is twice the highest frequency in the modulating signal. This is very important. This is our conclusion. So here we have seen that if my modulating signal is itself varying, and of course any signal the signal to be transmitted will have a varying frequencies. So while we decide the bandwidth of the transmission channel, we should take care of the bandwidth, that is the maximum frequency of the modulating signal. 2 times the maximum frequency of the modulating signal will be the bandwidth requirement for the amplifier which is going to transmit my modulated wave. So now let us take an example with some numerical values. So this is a equation of a modulated wave. So carrier wave which has been modulated. So here the voltage of that V is given as 5 into 1 plus 0.6 cos 6280 t sine of this much. So we have to, let us calculate the maximum voltage V max, this V minimum, the mu value, that is modulation index, then carrier wave frequency, what is the frequency of the modulating signal, what are side bands and the amplitudes of the side bands. Let us calculate all these things. So in order to calculate all these things, let us just some simplification let us do. Let us bring this 5 inwards. So it becomes 5 plus 0.6 into 5 is 3 cos 6280 t times sine 211 into 10 to the power 4 t, that is in volts. Now the general terminologies we used in our standard format was the modulated carrier wave. I denoted this by AC plus AM. I took it sine omega mt. We can take sine or cos, they are same thing. omega carrier T. So, omega carrier is here. So, now in order to calculate all these things, we have to compare these two equations. So, let us see what is this AC. We see AC is this 5 volts. A modulation, the modulating wave is here, you see 3 volts. Let us calculate then omega. So, omega m is given as 6280. That is omega m is 2 pi frequency of modulating signal 26280. Now, pi is 3.14, that is 6.28 Fm is equal to 6280. So, frequency of modulating signal becomes 1000 Hz, that is 1 kilohertz. Similarly, frequency of carrier wave you can see can be calculated by this equation. So, we will write omega c as 211 into 10 to the power 4, that is 2 pi f carrier wave, 211 into 10 to the power 4. So, Fc is equal to 211 into 10 to the power 4 by 2 pi, that is something, that value is, let us calculate. So, on calculation this value comes out to be 336 kilohertz. So, on calculation this comes out to be 336 kilometer. Please take note of all this. So, now you see here, let us see the frequency distribution. So, this is the frequency distribution, this is Fc, and the lower band is Fc minus Fm, and the upper side band is Fc plus Fm. This will have the amplitude, we say AC, and these two will have the same amplitude, and that will be equal to mu times AC by 2. So, here the lower side band Fc minus Fm becomes Fc, you see it is 336. So, that is 335 kilohertz, and Fc plus Fm becomes 337 kilohertz. So, these are the side bands present. Now, here mu will be equal to Am by AC. Am is your 3 by 5, that is 0.6. So, AC will be here, simply AC is 5 volts, and this mu times AC by 2 is 0.6 into AC is 5 by 2, that is 5 into 0.3, that is 1.5 volts. So, this will be 1.5 volts. So, the side bands will have a frequency, lower side band 335 kilohertz, the upper side band will have 337 kilohertz, and the carrier frequency Fc that will have a 5 volts, and the side band frequencies will be, voltages will be 1.5 volts. So, this we have seen by taking some numerical example. So, you see the frequency spectrum with the corresponding amplitudes in the amplitude modulated wave.